There are 118 elements on the periodic table. 92 of these occur naturally, others are made in science labs. Now, whilst some elements may appear to be similar, many have very different properties, like hydrogen, a reactive colourless gas, but helium is a very unreactive colourless gas. Fluorine, on the other hand, is a pale yellow, poisonous gas. Lithium, a grey reactive metal. Carbon, black graphite or diamond. Gold is yellow, soft, rare metal. Mercury is a liquid metal at room temp. Iron is flexible and hard metal. Copper is a flexible metal that's a great conductor of electricity. So sure, from 118 elements, we're getting different properties, but some of the elements have certain properties in common. Dmitry Mendeleev, a Russian chemist, actually used this fact when he organized the elements into the periodic table way back in 1869. He didn't know of all the elements at the time, but he left gaps in his table where he predicted atoms would be found and stated the properties they would have. Over the years, he was proved correct, as new elements were discovered which fit into the periodic table just as predicted. Mendeleev's table was so good that we still use it today. So the elements have different properties. That's because they're made of different atoms. But where did this whole idea of atoms come from? The idea started in 400-ish BC. Democritus, a Greek philosopher, thought that if you cut a piece of gold in half and then cut one of those pieces in half and cut it in half again and again and again and again, he figured that no matter how good your eyesight and how sharp your knife, there must be a piece of gold that is so small you actually can't cut it anymore. A tomos, indivisible, or atome, you can't cut. Unfortunately, people didn't take to Democritus's idea. Skip forward a couple thousand years, John Dalton, an English chemist, once again proposed that matter is composed of these tiny indivisible particles called atoms. He suggested they were just structureless indivisible spheres. But then 100 years later, Sir Joseph John Thomson, an English physicist, discovered the electron in 1897. He called it the corpuscle at the time, and he won the Nobel Prize in Physics, so good on him. We later changed the name to electron, but we now knew that atoms weren't indivisible. You could get smaller than an atom because these electrons that Thomson had found had come from inside the atom. He also knew that they were negatively charged. So Thomson's model of the atom is that electrons are stuck in a sphere of uniform positive electricity. We call it the plum pudding model because I guess if you're an Englishman, it looks like a plum pudding. A few years after that, a New Zealand-born physicist and chemist, Sir Ernest Rutherford, fired alpha particles, which are basically helium nuclei, at a very thin sheet of gold foil, only 10,000 atoms thick. Now, 10,000 sounds like a big number, but atoms are teeny tiny, so the gold foil was actually really thin. It was expected that most of these alpha particles would actually go straight through, and most of them actually went straight through. A few of them, on the other hand, got a bit deflected and some even bounced back. Now, this told Rutherford that most of the mass of an atom was concentrated into the very center, and that's where this positive charge was. Rutherford gave us the idea of nucleus, and he proposed that the electrons are orbiting around outside this positively charged nucleus, with most of the volume of an atom actually being empty space. 2 years later, a Danish physicist by the name of Niels Bohr was working on the maths of the hydrogen atom and then proposed what he had found to other atoms as well. And what he said was essentially electrons can't just be anywhere orbiting the nucleus. They have to be at certain distances from the nucleus. He gave us the idea of electron shells. A shell is an energy level. Electrons with more energy are further out from the nucleus. So Bohr said that electrons can be in this shell or that shell or the next shell, but they can't be found anywhere in between. Now, this is the model that we go with in school, the Bohr model of the atom. We actually know more now. Electrons can be found in between shells. According to modern quantum mechanics, it's all about the probability. So technically, an electron from one atom could actually be found on the other side of the solar system or even on the other side of the universe. It's unlikely, very unlikely, but statistically speaking, it could happen. So now we talk about probability clouds. But like I say, in school, we go with the Bohr model of the atom. So, atoms. Elements have different properties because they're made up of different atoms for each element. The atoms differ in the number of subatomic particles they have. Subatomic simply meaning smaller than an atom. Now, there are three basic subatomic particles that we care about. The proton has a positive charge, the neutron has no charge, it's neutral, and the electron has a negative charge. There are a whole heap of other subatomic particles, but these are the three that we care about for our atoms. Now, most of the mass of the atom is found in the nucleus. That's where we find protons and neutrons. The extremely fast-moving electrons orbit around the nucleus, and they take up most of the volume of an atom, but they have a very tiny mass. It's nearly 2,000 times smaller than that of a proton or neutron, so when we talk about the mass of an atom, we ignore the electrons. We know that they have mass, but it's negligible. The atomic number of an atom is the number of protons. Each element has its own atomic number, and it's this atomic number which determines what the element is. If you have an atomic number of 3, okay, you've got 3 protons, your name is lithium. If you have 79 protons, your name is gold. If you have 11 protons, your name is sodium. So it's the number of protons, that atomic number, that dictates what the element is. The symbol for atomic number is a capital Z. Mass number, symbol capital A, is the number of protons and neutrons added together. Remember, we ignore the electrons as they're so very, very tiny. Mass number is also called the atomic mass or the atomic weight. I would shy away from calling it atomic weight because if you forget the word atomic in your hurry, you're just going to say weight, and that is wrong. That's something different. Weight is a force measured in newtons. So call it mass number or atomic mass. Unreacted atoms have the same number of protons with positive charges and electrons with negative charges. So this makes the atom neutral overall. One way we can use atomic number and mass number is to determine how many neutrons in the nucleus of an atom. If we want to know the number of protons, well, the periodic table tells us that. It gives us the atomic number, the number of protons. The periodic table doesn't tell us the number of electrons, but we know that the number of electrons is the same as the number of protons. The number of neutrons, on the other hand, we have to work out. But the mass number is how many things in the nucleus, how many nucleons. The only options are protons and neutrons. So if you know the mass number and the atomic number, which the periodic table gives us both, we simply take the number of protons, the atomic number, away from the mass number, the number of protons plus neutrons, and that will give us how many neutrons there are in the nucleus. The electrons spin around the nucleus of atoms in shells. Each shell has a maximum number of electrons that it can hold. This number is given by 2n squared, where n is the shell number. So the first shell can hold up to 2 electrons, the second can hold up to 8, the third 18, etc. Electrons fill in the shells in order to form an electron arrangement or electron configuration. This electron arrangement is written as the number of electrons in the first shell, and then a comma, then the number of electrons in the second shell, a comma, etc. So the electron arrangement for boron, Z equals 5, so that's the atomic number is 5, the electron arrangement would be 2, 3. For sulfur, Z equals 16. Atomic number of 16 says it has 16 protons. We know that it will also have 16 electrons, so we put them into the shells. 2 in the first shell, that is full. Move to the second shell. We can put 8 into that second. That's now full. So we have 6 left. Let's start a third shell. The electron arrangement for sulfur is 2, 8, 6. Now, one thing to note is that although the third shell can take up to 18 electrons, the 19th and 20th electrons are actually placed into the fourth shell before we go back and fill up the third shell. So calcium, number 20, the electron arrangement would be 2882, but vanadium, number 23, the electron arrangement, well, would go to 2882, and then the extra 3 would come back and start filling up that third shell up to 18. So it ends up being 28112. An isotope is a version of an element with a different number of neutrons. So we have protium, deuterium, tritium. These are all isotopes of hydrogen. They're all hydrogen because they have an atomic number of 1. They all have 1 proton, and that determines what it is. 1 proton, your name is hydrogen. Most hydrogen doesn't have a neutron in the nucleus, it's just the proton in the nucleus, so it has a mass number of 1. But deuterium has a mass number of 2, tritium has a mass number of 3. Deuterium has a proton and a neutron. Tritium has a proton and 2 neutrons. So these are isotopes. They are the same element. They have all the same chemical properties, but they have different masses because the number of neutrons differs. Now, isotopes actually explain why an element can have an atomic mass, which is a decimal number. It's an average of all the different isotopes. So protium, the mass is 1, deuterium, the mass is 2, tritium, the mass is 3. If we average these all out, we get a mass for hydrogen of 1.00794. Now that's very close to 1, because most hydrogen, like 99.985% of it, is protium. It just has a proton, no neutron. Deuterium makes up 0.015% of natural hydrogen, and tritium, there are only trace amounts. So yeah, the number is very close to 1, but it's slightly above 1, because, like I said, it's the average of all the different isotopes of hydrogen. The number of outer shell or valence electrons that an atom has actually determines the properties of the element. Elements in the same vertical column of the periodic table, called a group, have the same number of valence electrons, and so have similar properties. Atoms of main group elements, which are groups 1 to 2 and 13 to 18, gain or lose electrons to give their outer shell 8 electrons, with a couple of exceptions. They gain or lose electrons by reacting with each other. For example, sodium, electron arrangement 281, and chlorine, electron arrangement 287. Remember, they're trying to get 8 valence electrons, 8 electrons in their outer shell. Sodium has 1 valence electron, chlorine has 7. Chlorine needs 1 more, and sodium actually doesn't want that 1 valence electron. If it got rid of it, then its outer shell would have 8. So it does get rid of it. Chlorine says, great, thanks, I'll pick that up. Adds it to its 7, and it now has 8 valence electrons. This makes the atoms more stable, having 8 valence electrons. This is called the octet rule, oct meaning 8. Remember I said there were a couple of exceptions. A couple of the lighter elements, like lithium, actually only want 2 valence electrons. They follow the duet rule. Now, group 18 elements, they tend to not do anything. The noble gases are very unreactive. Why is this? They already have 8 valence electrons. Atoms react in order to get 8 valence electrons. If they've already got them, they don't need to do anything, so they don't. Now, when an atom loses an electron, it's actually losing a negative charge, so the remainder of the atom becomes positive overall. And conversely, when an atom gains an electron, it's gaining a negative charge, so the whole thing becomes negative overall. These charged atoms are called ions. So sodium lost an electron, it became the sodium ion, Na+. Chlorine gained an electron, became Cl-. Now we don't call this the chlorine ion because the negative ions finish with IDE, so we call it chloride ion. The positive ions are called cations and the negative ions are called anions. And when writing ionic formula, the cation always comes first. So we talk about sodium chloride, not chloride sodium. We talk about dihydrogen sulfate, not sulfate dihydrogen. Now, speaking of that sulfate, that's actually what we call a polyatomic ion. These are collections of 2 or more atoms that have a plus or minus charge. Most common polyatomic ions actually have negative charges. This simply means that the ion has somehow picked up extra electrons, more than the individual neutral atoms that make up the ion. These extra electrons that have been picked up, and the extra negative charges, are shared by all the atoms in the polyatomic ion. When 2 or more different atoms chemically react, they form compounds. Now these compounds have very different properties from the original atoms in their element form. We use chemical formula to represent a molecule of a compound. They show how many atoms of each element were combined, and there's only one correct chemical formula for each compound. For instance, the chemical formula for water is H2O. Why is this? Because to make a molecule of that, you're going to need 2 hydrogen atoms and 1 oxygen atom, so H2O. Let's say you wanted to make some nitric acid. Well, the formula is HNO3. That means to make this nitric acid, you need 1 hydrogen, 1 nitrogen, and 3 oxygens. You want to make some sucrose? 12 carbons, 22 hydrogens, and 11 oxygens are what you'll need. Now, we use equations to show what's changing in a chemical reaction. They can be word equations or formula equations. The starting substances are reactants, and at the end we have products. For example, magnesium and oxygen, they react together to form magnesium oxide. Now there's this thing called the law of conservation of mass, which says that no atoms are created or destroyed in a chemical reaction. So when you're doing formula equations, they need to be balanced, so there are the same number of each type of atom on each side of the equation. So for the previous example, we would write 2Mg plus O2 gives 2MgO. The numbers in front of the formula state how many molecules there are. The numbers after each element symbol refer to how many of that type of atom are in each molecule. So 2O3 says 2 molecules of ozone, but 3O2 says 3 molecules of oxygen. Now, in both of these cases, there are 6 oxygen atoms, but they are bonded differently. Compounds do not have a charge, so any positive charge from the cation must balance any negative charge from the anion. When writing the formula for ionic compounds, we consider the size of the charge of the ions that make up that compound. If the size of the charge is the same, we simply put the ions together. For instance, the sodium ion, Na+, will react with the chloride ion, Cl-, to give us NaCl, sodium chloride. We know magnesium reacts with oxygen to give us magnesium oxide. The ions, Mg2+, and O2-, same size charge, simply put them together. So the formula for magnesium oxide is MgO. If, on the other hand, the size of the charge is different, all the charges won't cancel out if we just put them together. So we use the drop and swap method. Let's say we want to make some lithium nitride. Lithium ion is Li+, and the nitride ion is N3-. If we just put them together, we're going to be left with in excess of minus charges. So we drop and swap. The 3 from the nitride drops down, comes over to the lithium, and that gives us the formula Li3N. The 1 from the lithium ion actually drops and goes over to the nitrogen as well, but it's like algebra. We don't bother writing a 1. Another example, aluminium oxide. Al3+ is the aluminium ion, O2- is the oxide ion. The size of the charges are different, so we drop and swap. The 3 comes down and across over to the O, and the 2 comes down and across over to the Al, so we're left with Al2O3. That's the formula for aluminium oxide. Well, that's the video done. If you liked it, brilliant. Hit the like button, and leave me a comment too. Now you know what to do. Go hit that subscribe button. We'll see you next time.